Okay, number 7 says a charge Q1 of 25 microcoulombs. So let me do some writing down. So Q1 equals 25 microcoulombs. Moves with the speed of 4.5 times 10 to the third meters per second. Perpendicular to a uniform magnetic field. The force experienced by the charge is 7.31 times 10 to the minus third newtons. A second charge, Q2, is 5 microcoulombs, and it goes at an angle of 40 degrees with respect to the field, the B field. All right. And the force on that one is 1.90 times 10 to the minus third newtons. Part A says determine the magnitude of the magnetic field, and then Part B says find the speed of Q2. All right, well, let's look at Part A first. F is equal to BQV. So if I'm looking for B, I'm going to take F and divide it by QV. So everything is just a plug and chug. 7.31 times 10 to the minus third newtons. Q told me was 25 microcoulombs. And B was 4.5 times 10 to the third meters per second. So that should allow me to solve for B. And then when I did that and solved for B, I got 0.065 Tesla. Okay, Part B said, what is the speed of Q2? So I said, well, let's look at that. So F2 is equal to B Q2 sine of theta. Now, I didn't worry with sine of theta for this one, for Part A, because it told me it was a 90. All right, here they tell me, though, it's a 40, so I better worry about it. So I'm going to take F2, and I'm going to divide it by B, which I know, Q2, which I know, and this should have had a V in there, and sine of 40, and that should give me my V. So I'm going to take 1.9 times 10 to the minus 3 and divide it by my B, which is 0.065 Tesla. My Q, well, Q2 this time is 5 microcoulombs. My sine of 40. Make sure you're in the degree mode on your calculator and solve for V. So when I did that, I got V to be 9.1 times 10 to the third meters per second. Okay, so there's number 7. We're going to clean that one up and go on to number 8. So number 7. Going to roll on down to number 8. And number 8 says, a circular loop of wire rests on a table. A long straight wire lies across the loop directly over its center as the drawing illustrates. The current in the straight wire is increasing to the left. The current's flowing to the left. In what direction is the induced current, if any, in the loop, and give your reasoning. So what I did was I put my hand with my thumb pointing here, and I curled my fingers so I had X's on this side and dots on this side. Okay, so if it is increasing, then on the top part of the loop I have to generate a magnetic field that will increase out of the page. So I pointed my thumb up, curled my right fingers in that direction. Down here it's increasing out of the page, so I pointed my thumb, let me say that again, I pointed my thumb into the page, and when I did that my fingers curled in a clockwise direction. So these are going to basically cancel each other out, so no current is induced. All right, let's finish out the last one, number 9. A proton, so we know that it's positive, has a speed of 2.2 times 10 to the 6th meters per second. It's going to go into a region between two plates that are separated by a distance of 0.18 meters, so I call that my D, 0.18 meters. And a magnetic field exists, and it's perpendicular to the velocity of the proton. How big is the magnetic field? So my proton will do something like that and just miss that plate right there. So I said, well, it's going to have some circular motion, so I know that there's going to be F sub c, and it's equal to mv squared over r. And that F sub c is supplied by the magnetic field F sub b. So BQV is equal to mv squared over r. They're asking me to find B, so I'm going to cancel out that V. So if I take it a little bit further, B is going to be mv, because I have one left there, over br, over qr. So m is a proton mass, 1.67 times 10 to the negative 27 kilograms. V is my 2.2 times 10 to the 6 meters per second. My Q is 1.6 times 10 to the negative 19th coulombs, and my radius of my circular pathway is the distance that separates the plates, 0.18 meters. So I'm going to multiply those two together, and divide. And when I did that, I got my B to be 0.1276 Tesla. Okay, I'm going to stop that one, then I'm going to record those practice problems that will help you with the right hand rule.